Hi, in quantum mechanics, today we will discuss the conditions for physically acceptable wave functions. All right, we have talked about wave functions. All right, the question is whether all functions can be physically acceptable solutions of the Schrodinger equation. All right, so we'll see that not all wave functions, not all functions can be considered as a wave function. It needs to satisfy some properties. All right, so that's what we'll discuss today. Conditions for physically accepted wave functions, right? So I have put in many things in the first point. It should be finite, the wave function should be finite, it has to be single valued and continuous everywhere in space, all right? It has to be finite because we have a probability interpretation for this, all right? We cannot talk about probabilities unless we can, normalize it, etc. And if you want to talk about the probability of finding a particle at a point, it shouldn't be infinite there, all right? So it should be finite everywhere. It should be finite everywhere, and it has to be single valued, right? So corresponding to one point in space, you need to get only one complex number, right? Generally, it could also be a real number, but corresponding to the wave function should give you one number corresponding to every point in space, all right? It shouldn't give you two numbers for the same point, all right? Then it gets all confused. We cannot really use it. So what's the probability, if you ask? It should have a definite answer. So actually it tells us the probability amplitude, as we have discussed. So that the wave function has to be single valued means that at every point in space you have just one complex number, a unique complex number, all right? And it has to be continuous everywhere in space, all right? It has to be continuous. You cannot just have wave functions like that which are not continuous, all right? It should be continuous. It should go in a continuous, it should change, all right? The value of the function should change in a continuous manner when you move from point to point in space, right? But not only psi should be continuous, d psi by dx also should be continuous, all right? It should be continuous everywhere in space, okay? But there are exceptions, all right? Suppose if you encounter an infinite potential like this, all right? In that case, the wave function has to be continuous still. Wave function has to be continuous everywhere, all right? This is an infinite potential. Okay. So if this is an infinite potential, for example, we can talk about a particle which is trapped in infinite potential well, all right? In that case, we know that the wave function outside is 0 because the particle cannot be outside. There shouldn't be any probability of finding the particle outside of this potential well, all right? In that case, the wave function has to be continuous in the sense that it should become 0 by the time it reaches here, right? At the border, for example, it should be 0 because outside it's 0. Right? So the continuity of the wave function means that the wave function should be 0 at the boundary, right? But in this case, the gradient or d psi by dx, the derivative d psi by dx need not be continuous, all right? If there's an infinite potential value here, it need not be continuous here, all right? D psi by dx, but psi has to be always continuous, okay? So these are some of the conditions that we'll be using later on to find the wave function, right? We need to demand the boundary condition, we need to impose the boundary condition, and we'll use these properties. We'll say that, all right, psi has to be continuous, all right? So what does it tell? What new information does it give us, etc., right? So remember, if the potential is infinite, if at a point the potential is infinite, then at that point the derivative d psi by dx, right, d psi by dx can be discontinuous, right? But generally everywhere else it has to be continuous, okay? Now it has to be square integrable. So we are talking about wave functions, and we are talking about square integrable functions. What do we mean by square integrable? So if you take a range, right? If you take a range in which you are studying the physical system, or if you take the range in which the physical system is confined, so within that range, okay? For example, A to B. Suppose you are in one dimension, you are talking about points between A and B. All right. So in that case, the wave function has to be square integrable within these limits, all right, or within these boundaries. Right? So that means that square has to be finite. Okay, it's less than infinity, it has to be finite. Why should it be finite? Because only then we can use the probability interpretation, all right? So if it is finite, if it's a constant finite number, what we do is that we'll divide the wave function by this particular number, and then we have a normalized wave function, all right? Once we have a normalized wave function, the modulus square can be directly associated to the probability, okay? Okay, so in this case, this is the range minus infinity to infinity. This means in all space. Okay, this is the general case. Right, but this minus infinity to infinity need not be always there. The important thing is that it's the range of the wave function. All right, within what range we are talking about. This is all of space. Okay, generally this has to be true. Generally this has to be true. Okay, now but in specific cases we'll be using conditions like a to b, which includes this actually. All right, this minus infinity to infinity actually includes integral a to b. So when you solve problems, you may have to use a certain finite limit, right? But generally within all space, okay, this means that you should be able to normalize the wave function. Okay, only then we can work with Max-Born's probability interpretation. All right, let's look at some problems. All right, there can be problems asked like this. In fact, problems have been asked like this. All right, so which among the following is an acceptable wave function? All right, so they haven't given any range or something. They have just asked which is an acceptable wave function. Okay, and in this case we see that a secant x is 1 by cos x, but cos x can go to 0. All right, secant x is 1 by cos x, but cos x can be 0 for certain values of x. For example, when x equal to pi by 2, cos x is 0, then secant x becomes infinite. Okay, so there is a point in space where the wave function is not finite. Okay, that means that this is not an admissible wave function. It's not a physically acceptable wave function. And similarly, a tan x also, for example, it is sin x by cos x, right? And since cos x can be 0, where sin x is 1, for example, this also has an infinity at some point in space. All right, so psi of x is equal to a tan x is also, it also gives an infinite value. So these two cannot be acceptable wave function. What about a e raised to x square? Okay, so when you look all over space, you will see that when x equal to minus infinity and x equal to plus infinity, this also becomes infinity, because e raised to infinity is infinity. Okay, so this blows up at x equal to plus or minus infinity. That means that you cannot use this. Okay, so all these three options a, b and c are not finite everywhere. All right, there are points where the wave function becomes infinite. All right, it's not finite everywhere, so these are not acceptable wave functions. All right, these are not physically admissible wave functions, and obviously the answer should be option D. Right, you see that it's a e raised to minus x square. It's a e raised to minus x square. At plus or minus infinity, it becomes 0. That's fine. Right? So this is a physically admissible wave function. All right. Now the second one, which among the following functions represent physically acceptable wave function? Again, it's the same question. We have got 3 sine pi x, 4 minus modulus x, 5x, x square. All right. So if you look at this, f of x equal to 4 minus modulus of x, all right, this modulus of x, this is a bit tricky because at 0, it's continuous, the wave function itself is continuous at 0, all right, but the derivative causes problems at this point, all right, there's no unique tangent to this point, for example. Okay, so this is not a physically acceptable wave function for that reason. Okay, there are other reasons here, all right. So for example, in this case, yeah, in this case, you see that when x equal to infinity, this also goes up. Right? This also blows up. It also becomes infinite. So this is not finite everywhere. Not finite everywhere. Okay. And there's one more problem. The first derivative is not continuous. Is not continuous. Even though the wave function itself is continuous, the derivative is not continuous in this case. All right. You know there's a problem with the derivative at this point at x equal to 0. Okay. Similarly, h square of x equal to 5x, this is continuous, fine. The derivative, the first derivative is also continuous, there's no problem, but it becomes infinite. At x equal to plus or minus infinity, this becomes infinite. So this also cannot be accepted. The same is the case with rho of x equal to x square. It's continuous and all that, but it has it gets an infinite value. Okay. So the only option we are left with is this 3 sine pi x, all right. But if you take the full range of x from minus infinity to infinity, you will see that this is not normalizable in the sense that you cannot, this is not square integrable in the full range, integral minus infinity to infinity. If you take that range, this is actually not allowed, all right? It cannot be, it's not square integrable, right? Because it does not, when you integrate from minus infinity to infinity, it may not converge to a definite value. You can check that, right? Because this is an oscillatory function, it goes like that, it does not really converge to any finite value. Okay, so for that reason, this is not square integrable. Generally, this is not square integrable. Same is the case with wave functions like cos x. All right, it's not square integrable. Okay. But we can use this wave function in the cases where the range is not minus infinity to infinity. Okay, so there can be problems where we are interested in a range like minus a to a. For example, in square well potential that we'll see later on. All right, minus a to a. Right? So we are not talking about all space. So it's sufficient that it's square integrable within this region. It's square integrable within this region, and you will see that the wave function satisfies, this wave function satisfies that condition. All right. So if the range, in the question they haven't given the range, it's not a very well-defined question because they haven't given the range of x. Okay. So we assume that of all the options, option A is the best option. We have seen such wave functions, for example, in square well potential or particle in a box, we have such wave functions. But over the range of x is not minus infinity to infinity. It will be the dimensions of the box. The range of x will be the dimensions of the box. Okay. So the best option or the best choice among the options here is option A. So we have to choose that one. All right. Okay. So such questions can be asked where you may not be able to completely get all the requirements. So you look for the best option. So in this case, the best option is 3 sine pi x. In fact, we have seen such wave functions. For example, particle in a box, etc. Such wave functions exist. All right. So since there is nothing said about the range of the wave function, we can say that option A is the best answer. We've got more problems. Here, a ball bounces back off Earth. You are asked to solve this quantum mechanically, assuming the Earth is an infinite hard sphere. Okay, you have got Earth. This is an infinite hard sphere, which means that the ball cannot penetrate. Okay, the ball cannot penetrate, which means that the wave function inside has to be 0. All right, when you say that it's infinite hard sphere, it means that the ball cannot penetrate. So the probability for finding the ball inside will be 0. Okay, that's what it means. So the wave function inside will be 0. All right. Consider surface of Earth as the origin, implying v of 0 is equal to infinity. All right. So we'll take the point, the surface of Earth as 0. All right, and at this point v is equal to infinity. And a linear potential elsewhere, it's v of x equal to minus mgx for x greater than 0. Right. So you have got a finite potential elsewhere. Okay, but at the surface of the Earth, you have got an infinite potential. You are asked to imagine such a problem. All right, which of the following functions is physically admissible for this problem? All right, for k greater than 0. So in all options, you have got a k there. All right. So which of the following wave functions is physically admissible for this problem? Right. So we have to look at each one. All right. So we are given this information that when x is greater than 0, when x is less than 0, all right, when x is less than 0, the wave function has to be 0. So first we can check this condition. Okay. Of all these things, which wave functions go to 0 for x less than 0, right? So if you look at this thing, right, this has a problem because when you put x equal to 0, this becomes infinite. All right. So this wave function, the first option, this wave function has an infinite value at x equal to 0. So immediately you can get rid of that because we need to talk about the point x equal to 0. What about this one? It's a e raised to minus k x square, right? Where when x equal to 0, it's fine. But when x less than 0, this does not vanish. When x is less than 0, this does not vanish. All right. If you put a negative value for x here, it doesn't change. All right. So this is not equal to 0 for x less than 0, as you can easily see, if you put x equal to minus 1, for example, if you put x equal to minus 1, then it's a e raised to minus k multiplied by minus 1, so it's plus k. It's a positive number, not equal to 0. Okay, so this also cannot be the correct option. Okay, what about ax e raised to kx? Okay, this looks promising because at x equal to 0, this vanishes. At x equal to 0, the wave function is 0. But then the problem starts when x less than 0, it does not become 0. For x less than 0, this one does not become 0. Also, there's this problem that at x equal to infinity, so the range of the problem is from 0 to infinity. In this case, when x goes to infinity, all right, this blows up. So this also cannot be used. So the only option we are left with is option D. All right. Now, if you look at this, we have got ax e raised to minus kx square at x equal to 0. This is 0. All right. That means it's continuous. That means it is continuous. All right. We know that it's 0 inside. We know that it has to be 0 inside. All right. We can say that it's 0 inside, and for x greater than 0, it's this. Right. If it's 0 inside, at this point also it has to be 0. That's the continuity of the wave function. Am I right? We know that it's 0 inside, so that means that it has to be 0 also on the surface. Otherwise, the wave function is not continuous. In this case, it is continuous. At x equal to 0, it's 0. Right? At this point, we have to use some other function or just put it as 0. All right? And as x tends to infinity, what happens? This term will pull it down to 0. As x goes to infinity, this e raised to minus kx square, all right, it will pull it down to 0. Okay, so this is a physically admissible wave function. All right. Now this wave function, option B, has another problem. It's not 0 at x equal to 0. Actually, that's the point I should have emphasized. All right. This option B, it's not 0 at x equal to 0. Okay, so this is not continuous for our problem. Not continuous. Because we know it's 0 inside, it has to be 0 at this point also. All right. Okay. All right, the other things we have discussed. Actually, this is the point I should have emphasized for option B. Right, it's not continuous at x equal to 0. Right? Also, the other properties, it seems fine. All right, so the only problem with this is that it's not continuous. Okay, because the wave function has to be 0 inside. Right. Now, for negative values, we say that it has to be 0, but we can take the range of the problem from 0 to infinity. All right, we can take the range of the system that we are talking about from 0 to infinity. So you don't really have to check, as I said earlier, you don't really have to put a minus value and check whether it goes to 0. We can fix the range of the problem from 0 to infinity. But then there's a problem that this is not continuous. Okay. All right. So the correct option is option D. So I hope you are getting the idea of determining the physically acceptable wave function. The next problem is left as an exercise for you. Which of the following functions represents acceptable wave function of a particle in the range minus infinity to infinity? All right, the range is given. It's all space. All right, in one dimension, it's all space. It's from minus infinity to infinity. All right. Now you have to check which of these wave functions is physically acceptable. All right, this we already had ruled out because it gets an infinite value at some points. All right, we had already ruled out such wave functions. And what about this one? All right, what about this one? It seems it's all good. It's continuous. It is single valued everywhere. Okay. The problem here is it square integrable? All right, is it square integrable in the range minus infinity to infinity? All right, this is the thing you have to check. This is the thing you have to check. Okay. Now option C, here it's exponential minus d by x square. All right, but they have given here c is greater than 0, fine, but d is less than 0. D is a negative number. D is a negative number. All right, which means that minus d is positive. Minus d is positive. Okay, so at x equal to 0, you see that it will blow up because it's e raised to infinity. E raised to infinity is infinity. All right, so that should rule this out. Okay, you can look into the other properties if you want. And the only thing we are left with is phi of x is equal to ex, e raised to minus fx square. E and f are greater than 0, so it is fine. Okay, you will say that at infinity, all right, when x goes to infinity, this part e raised to minus fx square will ensure that it goes to 0. The wave function goes to 0. All right, so you can look into the details of that. Now, in some problems, all right, we haven't seen such problems yet in previous NET exams, but they can give you the shape of the wave function, all right? They can give you the shape of the wave function, okay, like this, and ask, okay, which among the following is the correct wave function, all right? So, one other kind of question that they could ask, okay, they could ask. Give me a moment. Okay, so one other kind of question that they could ask is just give you the form of the wave function, all right? Just give you the form of the wave function, all right? For example, they may give a wave function like that as option A. Okay, this is your x-axis and this is psi of x, all right? They may give you a wave function like this. Okay, again psi of x and x, right? They may give you a wave function like this. Okay, or let's say they give an option, how do you put it? Okay, I'll just give you an example here. Okay, all right, these are possible questions. All right, you are asked which among the following are physically acceptable wave functions. Okay, so if you look at this, you see that it's continuous, well behaved and all that, but there's a problem here. All right, at this point the derivative does not exist, or the derivative d psi by dx is not continuous. D psi by dx is not continuous in this case. In this case, all right, because if there's not a unique way of getting a tangent at this point. Okay, so this is not there. This is actually the function modulus x. We have already seen it. There is no unique way of drawing a tangent at this point, or d psi by dx does not exist at certain points, but d psi by dx has to be continuous. So you can't, you have to roll this out. Okay. Now what about this thing? All right. This thing looks a bit tricky. It looks like a good wave function, but here there's a point that we have not yet discussed. All right, because if it takes all the points, all right, if you drop a perpendicular to x, you see that at x equal to some x0, it has multiple values. Right, it has wave function has multiple values. All right, so this kind of wave functions is not single valued, not single valued, not single valued everywhere. Okay, so you have to discard it. I hope this is one thing that we didn't see it. See, for example, the functions like sine inverse x, or the functions like sine inverse x. All right, it's not single valued, because corresponding to x equal to 0, you can have functions like sine inverse of x for x equal to 0 could be 0, pi, 2 pi, etc. For example, okay, look at that. You can look at that. It will be something like this. Okay, it will be something like this. If you go for sine inverse x, you will see that it's not single valued. All right, so this is one thing you have to check. Also, this is not single valued. Right, see, at a point there are multiple values for the wave function. This is not allowed, as we said. Right, so the only option here is actually this. This seems to be a legitimate wave function. All right, this seems to be a legitimate wave function in the range given. All right, in the range given. Let's say the range is 0 to infinity. Okay. All right, so such questions also can be asked, right? So in examination, the problem you should be able to identify by carefully looking at the options. All right, here there's, for example, in this case, it's a bit tricky because they have given rather, see, it says that d is less than 0. Okay, if d was greater than 0, it would be a different story. If d was positive, it would have been a different story. All right, so these things you have to be careful. Okay. Now, later on in approximation methods also we can, for example, find approximate solutions by looking at a trial wave function. Right, you look at the problem and then you assume that, all right, the wave function may have such and such form. Okay, you can start with some trial wave functions and then find the parameters. This method we'll use in approximation methods. In that case, it's important that you make sure that your trial wave function is a physically acceptable wave function. Okay. All right. So with that, the problems involving checking whether the wave function is physically acceptable, I think that's enough. You can just understand this, look at these problems, and you should be able to solve problems of this kind. All right. It's important Now, just before concluding, let me discuss orthogonality and orthonormality conditions for wave functions. Okay, orthogonality and orthonormality. Okay, so we already discussed these things in the abstract vector space. You may have phi I, phi j is equal to delta ij, all right, or is equal to 0 for I not equal to j. In this case, we say that these are orthogonal. These are orthogonal, and we have already discussed that the eigenvectors corresponding to different eigenvalues for a Hermitian operator. Okay, eigenvectors corresponding to different eigenvalues are orthogonal. We have seen these things, all right. But in the function space, you just take a coordinate representation here. You can check this, all right. You just insert what do you say, an identity here in terms of the coordinate basis, etc. That's how we do this. We can see that this same condition, all right, or phi m, phi n, okay, the same condition in the coordinate basis or in the function, when we deal with wave functions, here these vectors are represented by wave functions. Okay, it becomes psi m star psi n. Okay, psi m star of x, psi n of x dx integral. Okay, this is the definition for a scalar product, okay, of wave functions. It's, if you want to find the scalar product of two wave functions psi and phi, okay, what you do, or psi of x and phi of x, okay, the one way to do is it is integral psi star of x, phi of x dx. That's how we find the scalar product of wave functions. Okay, right. So this is the orthogonality condition. Right. If these indices m and n, this could be discrete indices, this could be continuous indices, doesn't matter. Okay, if it's continuous indices, of course you could have written it as a function, functional dependence, but this is how we usually write it. All right, the functional dependence we write only x for the wave function, and the other things, for example, it could be momentum, it could be energy, the other things we write as a subscript. Okay, that's the usual convention that we do in quantum mechanics. So minus infinity to infinity, psi m star of x, psi n of x dx equal to 0. Okay, so this means that, all right, if a particle is in a state psi m of x, okay, psi m of x, if you make a measurement, there is no probability of finding it after the measurement. We know that after the measurement, the state of the system changes. So the probability that the state of the system changes to psi n of x is 0. That's one way of saying that they are orthogonal. All right, which also means that the psi m of x has no contribution from psi n of x. That's one other way of saying it. Right? And the probability of measuring the eigenvalue labeled by n is 0. Okay? If a particle is in the state psi m of x, then the probability of measuring eigenvalue labeled n is 0. Now, two wave functions psi m of x and psi n of x are said to be orthonormal. All right? This is just orthogonal. We say that it's 0 when I is not equal to j, but we don't say what happens when I equal to j. Am I right? So if you say that when I equal to j, it has to be 1, then you have an orthonormal. This is the orthonormality condition. All right. So we say that when m is not equal to n, this is 0, and when m equal to n, it has to be equal to 1. Right. If you make sure that this is satisfied, then we can say that psi m of x and psi n of x are orthonormal. Okay. So another way of writing it is in using the Kronecker delta. Okay. This means that it is 0 when m is not equal to n, and it is 1 when m is equal to n. Okay. All right. Okay. So with that, I think we can conclude today's session. We'll continue in the next class. Okay. Thank you.